Hello everyone, I'm Yanxue from Shanghai Jiao University. Today I will introduce our work, Shuffle-based private set union, faster and more secure. This is the joint work with Shi-Feng Sun, Hong-Sheng Zhou, Jiajun Dawu, and Dawu. I'm breaking my presentation down into 4 parts. First, I will introduce the what is private set union, PSU for short. Then I will summarize our contributions. Then I will further explain our main ideas. Finally, I will give a performance comparison. Let's start by taking a look at what is PSU. There are a sender and a receiver holding a set X and a set Y respectively. After the execution, the sender knows nothing, while the receiver can obtain the union of the set X and set Y, but knows nothing about the intersection. More specifically, given an item yi, if the item is in the intersection or the subtraction, is not allowed to be known by the receiver. In our work, we focus on the semi-honest setting. Before our work, most previous works are based on public key operations, so they are not efficient enough. And KRTW19 is the first and only PSU protocol that mainly relies on symmetric key operations and can support large datasets. However, in our work, we found that the bucketing technique used in KRTW19 will incur a security issue. Therefore, we designed 2 PSU protocols that are also based on symmetric key operations and achieve an improvement without using the bucketing technique. Also, we considered unbalanced datasets. Our 2 PSU protocols are individually applicable for different unbalanced cases. Finally, we perform a comprehensive evaluation and comparison. Let's move on to our main ideas. First, I will introduce a simple fact and then explain how we design our protocol based on this simple fact step by step. We assume that item y is shared to S1 and S2, such that y is equal to S1 or plus S2. Then given another item x, if x is equal to y, then x or plus S1 is equal to S2. Otherwise, x or plus S1 isn't equal to S2. Next, I will show how we take the above simple fact as a starting point to design our protocols. Let's first look at 1N PSU, which means that the sender only holds one item X and the receiver has a set Y that includes N items. And the receiver wants to know if X is in set Y. If X is in set Y, then the receiver cannot know anything more about the item X. Otherwise, the receiver needs to obtain the item X. More specifically, the receiver needs to know for each item yi if it is equal to item x without directly obtaining the item x. So we can use the above simple fact. The receiver needs to share each yi to 2 shares, Si1 and Si2. Then the receiver sends the set S1, including these shares, to the sender. Then the sender can use X to plus each share in set S1 to obtain the set I and sends set I to the receiver. We can see that if X is equal to yi, which means that X is in set Y, then Si1 or plus X is equal to Si2. So this intersection isn't empty. So the receiver knows that X is in set Y. Otherwise, the receiver knows that X isn't in set Y. If X isn't in set Y, because the receiver also knows this share, so the receiver can use this share to recover the item X. Otherwise, because the receiver knows Si2 is in this intersection, and the receiver knows that Si2 is the share of yi. So the receiver can know that yi is in the intersection. But in the PSU, this information is not allowed to be known by the receiver. So we need to change this step. The reason behind the issue is that the receiver knows the relationship between the items and these shares. So to solve this issue, we need to hide this relationship. We use the permute and share as a building block to generate these shares. More specifically, the receiver inputs the set Y, and the sender inputs a random permutation pi. After the permute and share, the two parties will obtain the shuffled shares. Because the receiver doesn't know the permutation pi, so given Si2, the receiver cannot know the original item Yi. Here I added the next step where the sender computes the set I and sends the set I to the receiver, and the receiver can use the set I to know if X is in set Y. If X isn't in set Y, then the receiver needs to obtain the item X. But here, because the shares are shuffled, so the receiver cannot directly recover the item X. So here we use the oblivious transfer to help the receiver to obtain the item X. And to guarantee that if X is in set Y, the receiver can just obtain a dummy item. But there is still an issue. If X is in set Y, the receiver knows set Y and share set as 2, and these two sets determine the share set S1 obtained by the sender. So the S1 cannot be used to hide the item X. Therefore, we need to add some secret key before computing the set I. Before computing set I, the parties additionally execute a multi-point oblivious PRF. Through multi-point OPRF, the sender obtains a key K that is not known by the receiver, and the receiver obtains the PRF values of his shares. Then the sender can use the key K to compute the PRF value for each item in the original set I and obtain the new set I. Then sends the new set I to the receiver, so the receiver can check if X is in set Y and obtain the item X or a dummy item as before. Now let's move on to the general case MN-PSU, where the sender also holds a set X with size M. The shares obtained by the sender are uniformly random, so that they can be used repeatedly for all the items in set X. Therefore, the permute and share and multi-point OPRF just need to be performed once. But for each item Xi in set X, the sender needs to generate a set II, and each II will obtain n items. So the computation and communication costs are both OMN. So we need to optimize the basic scheme. Our goal is to reduce the number of items in each set II. In the basic scheme, from the sender's point of view, any item in Y may be equal to Xi. So the sender needs to use item Xi or plus each share so that there are n items in each set II. So our key idea is to reduce the number of candidate items in Y that may be equal to Xi. We use the Kukuhashi to achieve our goal. Here I give an example to explain our optimization. The receiver first insert Y into the Kukuhashi table parameterized by Hashi functions H1 and H2. In our work, we set the stash size as 0 by adjusting the number of bins and the number of hash functions. We assume that for item Xi, H1 Xi is equal to 2 and H2 Xi is equal to 6, which means that Xi may be mapped to the second or the sixth bin. So only Y1 and Y3 may be equal to Xi. So the sender only needs to use the shares of Y1 and Y3 to generate II. This figure shows the optimization process. The receiver inputs the Kukuhashi table field by set Y to the permutation and share. And since the sender knows the permutation pi, so the sender can pick out the shares of Y1 and Y3, so that there are only 2 items in set II. After optimization, the overall cost of our protocol is O(n) log n, where n is the size of set X and set Y. In our work, we also consider the unbalanced datasets. In the protocol introduced before, shuffling dominates the course, and it is promoted on the receiver side. So the protocol isn't suitable for the case where the receiver side is much larger than the sender side. In our work, we also design a dual version, which shuffles the sender side. When the sender side is smaller, the dual version is more suitable. If you are interested in it, please refer to our paper for more details. Last, we compare our protocol with KRTW19. We can see that for large datasets, we can achieve a 4 to 5 times improvement in runtime. As for the communication, we can save 15%. The work by Gary Mella is a concurrent and independent work. They also achieve an improvement over KRTW19, but because they also use repetitive polynomial interpolations, their protocol is about 2 times slower than ours. This link refers to the full version of our paper. If you have any questions, feel free to contact me. That's all. Thank you.